In March 2018, NASA engineer Shannon Zerbel stood in a sterile white room at Brigham Young University, holding what looked like a child's paper airplane. Except this wasn't paper. It was a prototype solar panel that would soon power spacecraft millions of miles from Earth. The panel measured just 6 inches folded, but when Zerbel pressed a single button, it unfolded into a structure spanning 12 feet across. Perfect symmetry, zero mechanical failure. The ancient Japanese art of origami had just solved one of NASA's most expensive problems. Space is brutal on equipment. Every pound launched into orbit costs NASA approximately $22,000. Solar panels, the lifeblood of any spacecraft, traditionally required massive structures that barely fit inside rocket fairings. The International Space Station's solar arrays span the length of a football field when deployed, yet had to be folded into segments small enough to launch aboard the space shuttle. Each folding joint represented a potential failure point. Each mechanical hinge could jam in the vacuum of space, turning a billion-dollar mission into floating scrap metal. NASA had been wrestling with this problem for years. Traditional engineering approaches hit the same wall repeatedly. How do you create something enormous that starts impossibly small, deploys flawlessly, and never breaks? The answer came from the most unlikely place imaginable. A Japanese scientist was folding paper. Koryo Miura, an astrophysicist at the University of Tokyo, had been studying origami since the 1970s. But he wasn't making art. He was discovering that every crease in traditional origami follows precise geometric rules. These rules, when translated into equations, could solve engineering problems that had stumped NASA for decades. In 1985, Miura published his breakthrough, the Miura fold. This pattern could transform a flat sheet into a structure that folded down to 1/8 its original size while maintaining incredible strength. Japan's space agency immediately adopted Miura's design for their satellite solar panels. American engineers dismissed it as a novelty. But Robert Lang saw something different. Lang had spent 20 years as a laser physicist at Caltech before abandoning his career to become a full-time origami artist, which sounds insane until you realize what happened next. By 2008, he was consulting with NASA, Lawrence Livermore National Laboratory, and the German Space Agency. But Lang wasn't teaching them how to fold paper cranes. He'd discovered something that would make traditional engineers question everything they knew about physics. Origami mathematics could predict exactly how materials would behave under stress. Every fold created predictable angles. Every crease distributed force according to mathematical laws that had existed for centuries, laws that modern engineering had completely overlooked. Here's what blew their minds. Traditional mechanical hinges required lubrication, springs, and complex motors. Origami structures moved using only the material's own memory. No moving parts, nothing to break, nothing to fail. Lang had just handed NASA the holy grail of space engineering, and it had been hiding in plain sight for 1,000 years. The revelation struck Shannon Zerbel during a 2012 conference at MIT. She was presenting her research on deployable space structures when Lang demonstrated a simple origami flower. As he folded the paper, Zerbel realized she was watching the solution to every deployment problem NASA faced. The mathematics were identical to the stress calculations she'd been running for years, but origami had solved them centuries ago. Zerbel immediately changed her research focus. She began collaborating with Lang to translate ancient folding patterns into space-grade engineering. The breakthrough came on September 15, 2016, in a laboratory at Brigham Young University. Zerbel and her team had spent 4 years perfecting their design when something went wrong. Their origami solar panel deployed too fast, in just zero point 0.3 seconds with zero mechanical assistance. They thought they'd broken it, but the structure had locked into place using only the memory of the fold patterns, exactly as designed. The real shock came in NASA's thermal vacuum chamber. After 10,000 deployment cycles through space-like temperature extremes, the panel showed zero wear. Traditional mechanical systems died after 1,000 cycles. They'd accidentally created something indestructible. The implications staggered NASA administrators. Origami mathematics could potentially reduce launch costs significantly. Spacecraft could carry solar panels 5 times larger than current designs. Mars missions, previously limited by power constraints, suddenly became feasible with compact panels that deployed to enormous sizes. The mathematical principles discovered in ancient Japan were reshaping humanity's expansion into space, but the applications extend far beyond solar panels. NASA's James Webb Space Telescope, launched in December 2021, uses origami principles to deploy its massive sun shield. The shield protects the telescope's instruments from solar radiation, but had to fold into a package small enough to fit inside the Ariane 5 rocket. Traditional engineering would have required hundreds of mechanical joints, each representing a catastrophic failure risk. Instead, NASA used origami mathematics to create a deployment sequence using just 18 actuators. The sun shield unfolds like a cosmic flower, following crease patterns that ensure perfect alignment every time. Zerbel's team has since developed origami antennas that expand from briefcase size to structures larger than basketball courts. These antennas will enable deep space communications that were previously impossible. The European Space Agency is exploring origami mathematics to design habitats that astronauts could deploy on Mars. The structures pack flat for transport but unfold into multi-room living spaces. The transformation represents more than engineering innovation. It demonstrates how ancient wisdom can solve modern problems in unexpected ways. Origami masters spent centuries perfecting folding techniques through pure intuition. They discovered mathematical principles that Western science wouldn't formalize until the computer age. Japanese paper folders had been practicing advanced topology for generations without knowing the mathematical terms. Now their artistic insights are powering humanity's greatest technological achievements. The irony is profound. NASA spent billions developing complex mechanical systems to solve problems that Japanese artists had already solved using nothing but paper and patience. The mathematical principles behind origami reveal fundamental truths about how materials behave under stress. Every crease represents a calculated distribution of force. Every fold creates predictable geometric relationships. Ancient art had become cutting-edge science. Today, Shannon Zerbel is a key researcher in NASA's origami engineering efforts at Brigham Young University. Her team collaborates with origami artists worldwide, translating their intuitive folding techniques into mathematical models. They've developed software that can predict how any origami pattern will behave in the vacuum of space. The program has revolutionized spacecraft design, enabling structures that seemed impossible just a decade ago. Missions to Jupiter's moons, previously constrained by power limitations, are now being planned with origami solar arrays that will unfold to unprecedented sizes. The next frontier involves active origami structures that can reconfigure themselves in space. These designs would allow spacecraft to adapt their shape for different mission phases. A probe traveling to Saturn could optimize its configuration for the journey, then transform itself for orbital operations. The mathematics of origami provide the framework for this shape-shifting technology. The paper airplane that Shannon Zerbel held in 2018 has become the foundation for humanity's expansion across the solar system. Ancient Japanese wisdom merged with modern engineering has solved problems that stumped NASA's brightest minds for decades. Sometimes the most advanced solutions come from the most unexpected places. What other ancient arts are hiding the keys to tomorrow's greatest challenges?